Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. Today's topic we will see the finite volume formulation and the scheme for the convection terms, and that is for 2D and 3D flows. In the previous classes, we have seen the diffusion term finite volume formulation in 2D, 3D, and we have seen whether the source terms will change the phenomena or not, and then we have also seen how different the finite volume formulation is when compared to the finite difference. Okay, so let's have a quick recap and then let's go for the convection terms. Okay, so here already we have seen, so from the past two sessions we are seeing the same formulation, which is the surface integral. So here we have the surface integral, and then we have the surface integral for the diffusion term. This is for convection term. So we have clearly seen about the diffusion term. So and we have embedded the source term. So you can see this is LHS and this is RHS. Okay. So we have the combination of LHS and RHS, where you can see that the balance should be present in between the convection term and the diffusion term. So if there is a proper balance between the convection and diffusion, then you can actually properly define the flow. So how, if the diffusion is increasing, the convection should come down, or let's say if the convection is increasing, the diffusion will come down. Okay, already we had seen previously Reynolds number, which is rho VL by mu. So here it is a ratio of inertial force to the viscous force. So the inertial force is like it's relating to the convection terms, and the viscous force. Okay, so here if we relate these numerator and denominator, so what is happening? So if the Reynolds number is high, the convection term is high, and the viscous term is low, or the diffusion term is low. So the viscous effects or the viscous forces are the major phenomena, so which is causing the flow very diffusive. Okay, that is one thing. Now, so when the Reynolds number is increasing, the viscosity effects and the diffusion terms will decrease. When the Reynolds number decreases, so the viscous effects will increase, and the diffusion or the convection will decrease. So example we can take honey. Okay, so honey is a highly viscous flow, so we cannot actually have more convection for the honey. Why? Because so the viscosity of honey is very higher. Fine. So that is why. So we will actually say that the diffusion is very high for the honey, and the convection is less. Fine. And other thing, you can take it as air or water, where even though you cannot swim in honey, but you can swim in water. So where the viscosity effects when compared to honey and water, so honey has more viscosity nature and diffusive, less convective, and the vice versa is applicable for air. Fine. So this is what is being seen. Now, when for the finite volume formulation, we had seen the RHS, which is the diffusion and the source term. So we need to see the convection term. So basically, what we are seeing, we need to see so rho u, like what is it, rho phi u, right? So rho phi u, phi is any flow variable which we have. So phi is nothing but it's a property where you can say it is pressure, density, temperature, velocity, anything can happen. Okay, so this is what we have. So we have already seen that finite volume formulation is much suitable and for the complex geometry, and the integral form of equations are used for the finite volume method. Whereas if we see finite difference method, we use differential form of equations. Okay, so we didn't see any integral parameters or the integration parameters in the finite difference method. For finite volume method, we are seeing the integral parameters. Okay? This thing already we have seen the sign convention, the notation. So here there is a conversion factor where so the volume integral is changing to the surface integral. Fine. So you have the conversion between the volume integral to the surface integral. Or here you can see surface integral to volume integral. So that is by Gauss theorem. So where we can say that whatever the changes that is happening, okay, through the flux can be related to the volume. So this is done using Gauss approach. So here you have n dot, here you have divergence. Okay. So n is nothing but your normal vector, so which is related to the flux, and div is nothing but so you have the divergence. Fine. So that is what. Here you have the source term. Okay. Next, so we are already seen the 1D 2D effects of FEM. So what we have seen, this is AP phi P is equal to AE phi E plus AW phi W. So this is what we have seen for the 1D flow. So for 1D flow, what is the terminology? So we have this cell. So this is the point of interest P. So here we have west node, here we have east node. So therefore what is happening? So whatever the dependency of point P we have on W, so we are giving here, okay, and on E we are giving here, right? So this is for 1D. So for 2D what we have done? So we have drawn here. So we have taken the point. We have taken this point. So here we have what? West node. Here we have east node. Here we have north. Here we have south. Okay, this is the point of interest P. Fine. So for this word formulation we have seen. So we have seen AP phi P is equal to AE phi E plus AW phi W plus AN phi N plus AS phi S. So AS phi S. So here what is happening actually? So AP phi P. So phi P is nothing but so the value of the property phi. Phi can be pressure, temperature, velocity, density. So these things. So that value at this particular point. And here you have east node, west node, north and so on. So the dependency is coming from all four neighboring points. So when you compare 1D and 2D, what is happening? So for the 1D, so we have only two neighboring points. For 2D, we have four neighboring points. Now we will see for 3D actually. For 3D, how the formulation changes, we'll see. So if you draw a 3D block, so when we draw a 3D block, what happens? So let's say at the center we have point of interest P. Okay. So at the back, so let's say we say back. So here we say F front. So at the side we have west node. So at the E you have east node. At the top, so you have north. At the bottom you have south. So here what is happening? The point of interest P. So P is surrounded by. So we'll draw here roughly. So P, which is with west node, P, which is with east node, and here you have north. Here you have south. Okay. So this is the point of interest P. This is for 2D. And additionally, what we are having? So here we have back. Here we have front. Fine. So west node, east node, north, south. So we have back and front. So these things are basically available for 3D. So this is for 3D. For 1D, what we have? only west and east. For 2D, what we have? West, east, north, south. For 3D, what we are having? Additionally, we have back and front. Fine. So this is the difference. Now, what would the equation change? So the AP phi P is equal to AE phi E plus AW phi W plus AN phi N plus AS phi S plus. So these two are for 1D. So this combination is for 2D. Now whatever additional thing we are doing, so what we have? A, let's say back phi B plus A F phi F. So this total thing is coming under 3D. So that is the difference. Fine. So we have 1D, we have 2D, we have 3D. Fine. So now what is happening actually when we are checking into these parameters in detail? So the dependency of phi, let's say phi P, or let's say the phi E, phi W, phi N, phi S, phi B, phi F. So it is going to increase. So when we take, so this is for only diffusion terms we are doing. So it's for only diffusion. So next, additionally, you have convection also. So whatever the 1D, 2D, 3D we have seen, that is for only the diffusion. So when we see for convection, so what do we have for convection? So let's say uh, we have the equation. So this is what convection equation we have. So it's n dot rho phi dx. So this is what we have. So what do we have? It's like rho u dA integration, let's say. Or so this is what we have. We can take it as phi. So this is what we have. You can see rho u phi dA. So if you take this unit vector n, so that will give the direction. So this surface integral. So this is what we have. So here what we will assume simplify is, so Fc, which is nothing but the convective force, or let's say the convection. So Fc is nothing but rho into u. Okay. So we have two things: Fc of W, which is of west side, and Fc of east side. Now, when we take the 1D, so we are seeing the convection phenomena for 1D first. Okay. So what is happening? Here you have west, but here the area is west surface. Here you have east. So the point here it is E. Okay. P. Fine. So small w, so capital W, capital E, small w, small e. Fine. So this is what we have. Now what is happening? So when you are seeing this left side, so one important thing is for the convection term. So when we are performing the equations, or let's say when we are writing the equations, so in which direction the convection is happening is important. Let's say the flow is coming from left to right. Okay, now what is happening? So it is coming from left to right. Here the relative convection will be, let's say, Fc, which is nothing but FCW plus. So this is what we have. This convection will come. Fine. So these things we'll see in detail. But let's see first initially how to do the finite volume formulation. So for the convection term, that's it. Now what we are seeing, we have seen clearly a row of phi u dA. So where the flux is seen at the west face and the flux is seen at the east face, both west face and east face. Fine. So here what happens actually? So when you integrate, so rho phi u so which is at east face minus rho u, sorry, rho phi u, west face. Okay, so the a, if the area is constant, we will take the area a. Fine. So here what we are applying, so rho into u is f. So we say it is flux. So flux constant, or let's say the flux amount. Okay, so this equation is changed such that f of phi at east face minus f of phi at west face into a. Okay, so this is what happens. So let's actually join the combination of convection and diffusion. Let's see. So what is happening? So let's write the full form equation. So f of phi into e minus f of phi w into a, which is equal to we have ap so the diffusion term. So ap phi p minus so ae, or we can write with the total terms. So where we have gamma p plus gamma e by delta x PE into phi p. Okay, so let's say phi e plus so on. So we have plus source term s of psi plus s of s plus s of psi plus psi. So here similarly you have for this. So this is the full form of general. So when we combine the convection and diffusion, so the equation is tend to modify in this way. Fine. So what is happening? So f of phi of e is modified, f of phi w is modified, and so we have to actually combine these two. Fine. So we are writing individually, but we have to combine these two. But in today's model, we are very much interested in convection. So this is for 1D, so convection. So for 2D, so what is happening? Same the element we have to take. So what do we have? So we have point of interest P. This is at the east, sorry. This is at the west. This is at east. This is at north. This is at south. Okay. So what formulation we have? So when we do the integration, so we have from west to east face. So which rho phi u dA plus we have south to north, which is rho phi u dA. So we have west to east, we have south to north. So this is what we have. So when we go, or when we actually rewrite the equation, so what is happening? Rho phi u into e minus rho phi u of w. So if you take the area common, so that will be what is it? That will be applicable for both the terms. This is term 1 and this is term 2. So this is of 2D. So area along let's say this west and east same. So what is happening? Let's say A is equal to A of east face is equal to A of west face is equal to A of north face or A of south face. So if we have this assumption, then you will take common in that as A. Fine. So this is what happens for first term plus second term. What we have? So we have rho phi u, so which is at the north, minus rho phi u, which is at south, into A. So when you have area change, let's say only in one direction, and let's say you have along x direction you have one area, along y direction you have. So you can take it as ax, ay. Let's say it is not same, ae is not equal to this one, not equal to, not equal to, not. So at each and every place we have to multiply it with particular area. Okay, this is what we have convection term for. So this is for convection term for 2D. Now, so when you take the same convection term for 3D, so 3D what is happening? So we will draw the block again. So we have drawn the block. This is the point of interest P. So this is the west. This is the east. This is the north. This is the south. This is front. This is back. Okay. So what is happening? So we have integration where w small w e, which is of rho phi u into dA, plus next south to north rho phi u into dA, plus we have integration. So we have front to back, okay, which is of, or let's say we can take back to front rho phi u to dA. Okay, so finally what happens actually? So here the formulation will be, so rho of phi into u of e minus rho phi u w. So this is for the first term. So basically you can take it as 1D. So the combination of this thing will give us 2D. So what we have, rho phi u of north minus rho phi of u south. So this combination is 2D, plus rho phi u, which is of front, minus we have back. Okay, so which is of rho phi u back. So everything so will be multiplied with the area. So this is total 3D. Fine. So this is what we can see in clearly that for 1D, so we have similar to the diffusion constant or the diffusion parameter. So we have two dependent parameters. For 2D we have 4 dependent parameters. For 3D we have 6 dependent parameters. So the thing is, so for the now the terminology is phi of u is written as f. So to reduce the length of this thing. So here what happens, the equation f u e minus f u w. So f is nothing but the flux quantity. Okay. Now, so in the next sessions we will see in which direction the flux is coming and how does the equation get added advantage. Let's say when we have the flow coming from left to right. So from left, so let's say we have some flow coming. So from right, so what happens, relative velocity, how does it change? So here how does it change? Okay, the convection and diffusion parameter, how does it change? So those things we will see. Okay, so in today's session we have seen basically the 1D, 2D and 3D of convection parameters for the finite volume formulation. The next session we will see in detail so of the combination of convection and the diffusion and the numerical approaches, and we'll take sample tutorials also. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.